So this is the worksheet that says page 250 on top, chapter 6, ratio, proportion, and variation. And the first 6 up there, they're just looking for missing links. So even though these are 2- and 3-dimensional figures, we're still looking for links. So it's just a flat out ratio of links. For like number 1, pretend my pictures actually are good. So we've got a triangle with sides 2, 4, and 5, and this is A, 3, and B. Now this one you said you got a lot of fractions or decimals. This one will come out to decimals.
Okay.
What 2 sides match up that we know the length from both figures? The 4 and the 3 match up. So we have 4 to 3 is a known ratio of sides. Now let's say we want to find A. Where's A going to go, top or bottom? Bottom, because it's from the same triangle as the 3. What's going to go above it?
When you set that up, Todd, does it matter top or bottom as long as they all stay?
Yeah, I'll show you in just a second here. So what matches up with the A from the other figure? The 2. So we can cross multiply and divide. This is 1.5. Now what if you had done 3 to 4 instead of 4 to 3? Well, then the A has to go on top because the A goes with the 3. 2 on bottom. Notice it's still 3 times 2 divided by 4. It's the same numbers even, just in different locations. And the calculation itself is exactly the same. In fact, you could even set it up like this as 4 relates to 3. And then, A is with the 3 and 2 is with the 4. It's still 2 times 3 divided by 4. So now we've got the 4 to 3, or whichever way you want to set it up. We need to find B. Where's B go, top or bottom? Still on bottom, still from the same figure as the 3. What goes above it? 5. So we're going to cross multiply. 3 times 5 is 15. Divided by 4 will be 3.75. So you're good on 1. Okay. Number 2. Let's see here. We've got I'm not going to draw out the figures, but we've got a 9 to 15 equals A goes with the 9 to 13. So 9 times 13 divided by 15. 7.8. Okay. So we've still got 9 to 15. B is going to go on top because it's from the 15, and 2 will go below it. 9 times 2 divided by 15 is like 1.2. What's that?
I don't know. I got 3.33.
3.33. Let's see. Did I set something up wrong? We're at 9 to 15. B, yep, I set it up backwards. B does not go with the 9, does it? B goes with the 15. And above the B would be the 2. So you are absolutely correct. 15 times 2 is 30, divided by 9 is 3.33. Number 3, what's our pair of sides that have the length for both figures? 34 to 66. Good.
That's simplified.
8. Yeah, it simplifies to 17 over 30. A is going to go top, and it'll be over 33. So 17 times 33 divided by 30 is 18.7. For B, we're at 17 to 30. B is going to go on bottom.
Wait,
Should be 17 to 33, shouldn't it?
wait a second. Yeah. Okay. On that one,
I don't know what I did wrong.
66, not
66, not
So
60.
it comes out to be 17 exactly, I believe.
Yeah, this should be 17 here.
Right.
Okay, I got to wake up for the morning. So it's 34 to 66 is actually the ratio,
Yep.
which reduces to 17 to 33. So 17 over 33 equals A over 33. Well, A has to be 17. So then we've still got 17 to 33. Bless you. B is going to go on bottom, and it'll be 22 to B. So 33 times 22 divided by 17. 42.71. 0.7 works. And then C, 17 over 33. C goes on bottom, and it would be over 24.3. So 33 times 24.3 divided by 17. 47.2. Close enough?
47.17.
Yeah. Okay. Anybody need me to go over any more of those? You guys feel comfortable 1 through 6?
No, I'm good.
Okay. Now, 7 through 16 is where it gets tricky. Number 7. Talking about floor plan of a building has a scale of 1/8 inch equals 1 foot. So in architecture, remember we talked about that, is you have a 1/8 scale means 1/8 inch equals 1 inch. In architecture, a 1/8 scale means 1/8 inch equals 1 foot. So this ratio is not 1/8 to 1, it's actually 1/8 to 12, because 1 foot is 12 inches. Or it is a 1 to 96 ratio. You might wonder, where did the 96 come from? Perfect. Yes, 1/8 over 12, and to get rid of the fraction, we're going to multiply by 8 to get 1 and 96. Perfect. On the floor plan, the room has an area of 20 square inches. What is the actual area? Well, the ratio of lengths is 1 to 96. How do we get a ratio of areas off of the ratio of lengths? We square it. 1 squared, of course, is 1. 96 squared is a big number, 92/16. So if the ratio of lengths is 1 to 96, the ratio of areas is 1 to 9,216. The 20 square inches is from the drawing. So that goes on top with the 1. So it's basically 20 times 9,216. Or 184,320 square inches. Now, of course, we don't really want the area in square inches. We want it in square feet. How do we convert square inches into square feet? Don't multiply. Divide by not 12, but 144. Good. It's square inches and square feet, so it's 12 by 12. So we'll divide that by 144. Gives us 1,280 square feet. Anybody get that one right? Anybody try that one? Okay. So that one's pretty straightforward. When you're dealing with a scale drawing, of course, you know you're dealing with areas. But now for number 8, it's a little foggier. At a wastewater plant, a pipe at a sewage treatment plant is 75 millimeters in diameter. It discharges 2,000 liters of water in a given period of time. They want to adjust the size of the pipe so that it can now discharge 3,000 liters in the same amount of time. What's the new diameter have to be? Well, the question we have to ask here is this an area problem or a volume problem? At first sight, it looks like a volume. They're saying 2,000 liters to 3,000 liters, right?
Right.
But they're asking us to change what? The diameter of the pipe. Does changing the diameter of the pipe change the volume? No. It changes the area of the pipe. The cross-sectional area of the pipe is what it changes. It doesn't change the length of the pipe at all. Does that make sense? The flowage through that pipe is determined by the area of the cross-sectional area of the pipe. The length of the pipe doesn't mean anything. For this to be a volume problem, all 3 dimensions would have to be changed. Changing the diameter changes it in 2 dimensions, but it doesn't change the length at all. So the flowage, the volume of sewage that goes through this pipe is determined by the cross-sectional area. So even though it's a volume that we're trying to change, what we're adjusting is an area. So this is an area problem. So we want the ratio of volumes to go from 2,000 up to 3,000, which is a 2 to 3 ratio. This is the ratio of areas. How would we get from the ratio of areas to a ratio of lengths? Well, if we had the lengths and we wanted to go to the areas, what would we do to the ratio of lengths? We'd square it. Well, now we're going the other way, so we have to square root. Yes. So it's the square root of 2 over the square root of 3. We have a 75 millimeter diameter, which is the smaller one. So this is now going to be the square root of 3 times 75 divided by the square root of 2. 91 point, what does it say to round to? Does it say anything? What is this diameter? So we're just going to go 91.9 millimeters. This is always kind of amazes some people. We're taking that up. We're basically increasing the area of that pipe by 50%. We're going from 2 up to 3. But the actual diameter only goes up by a little bit, by less than, basically 20%, a little more than 20%. Okay. So as you can see, the difficult part is figuring out whether it's an area or a volume problem. Number 9. Square bar of steel, 38 millimeters on the side, has a mass of 22 kilograms. What's the mass of another bar the same length that measures 19 millimeters on each side? Area or volume? We've got a bar. It is 38 millimeters on the side, like this. We don't know the length, but we do know the length doesn't change. Now we've taken the sides down to 19 millimeters. Did all 3 of the dimensions of this change? No. All it changed was the length and width here, right? So all that changed was a cross-sectional area. To be a ratio of volumes, we must change all 3 dimensions according to that by the same ratio. We didn't change the length here at all. This can't be a volume problem. But we did go from 38 down to 19, which is a 2-to-1 ratio. That is the lengths still. So turn that into a ratio of areas. We're going to square it, so it's a 4-to-1 ratio of areas. And since the mass is going to be determined by the volume, but the length doesn't change, so we can use the areas to relate the mass. The 22 kilograms is the larger piece, so 1 times 22 divided by 4 will give us 5.5 kilograms for the smaller piece. Questions? Some of you look confused.
I skipped a little step along those.
The squaring and stuff? Okay. I think that number 8 was the toughest one because we didn't really go over any examples where you had to root it to get back to the lengths. Oh, let's see, 10. Yeah, we'll skip 10. Let's go up to number 12. A water tank that's 12 meters high. So it's 12 meters high. Don't know much else about it yet, so I'm not going to draw much in. It has a volume of 20 kiloliters. Or 2,000 liters, or 20,000 liters. What is the volume of a similar tank that is 30 meters high? So the height has gone from 12 up to 30. I'm going to reduce that. Both of those can be divided by 6. Give me a 2-to-5 ratio of lengths or heights. But now it's saying what is the volume, and is the whole, have all the dimensions of the tank changed by the same proportion? Yeah, it says a similar tank, which means it's been an enlargement of the other tank. So every dimension changes by that same proportion. So we're going to go to a ratio of volumes, which means we have to, not everybody at once, cube it. There we go, to the 3rd power. What's 2 to the 3rd power? 8. 5 to the 3rd power? 125. So the ratio of volumes is 8 to 125. Where's the 20 kiloliters go? Is that with the smaller tank or the bigger tank? Smaller. So you'll cross multiply and divide. 20 times 125 divided by 8 gives us 312.5 kiloliters. So you can see there we run into a volume. Okay. Any questions so far? Let's jump to number 15 then. On number 15, they're looking at a sphere made out of sheet metal. It has a volume 4,188.79 cubic centimeters. Surface area 1,256.64 centimeters squared. Find the surface area of a sphere. See, this has a radius of 10. Gotta put that in there, that helps. What would be the surface area of a sphere with a radius of 2 centimeters? Now, we could just use our formula for surface area if we wanted to, but for those of you that don't remember that from last semester, we can use the ratios here. We have a 10 to 2 or a 5 to 1 ratio of radiuses, or ratio of lengths. To compare surface area, squared or cubed? Squared. So it's a 25 to 1 ratio of surface area. Where does the 1256 go, top or bottom? Well, the larger one, so that goes on top, the larger number. And you cross multiply and divide. So 1256.64 times 1 divided by 25, 50.27 centimeters squared. Now it's saying find the volume of a sphere with radius 2. So again, it's a 5 to 1 ratio of radii. But we're trying to make it into a volume, which means we're going to go to third power cubed. So that's 5 to the third power is 125, 1 to the third is 1. So it's a 125 to 1. So the volume of the 4,188.79 centimeters cubed goes on top. So it's 1 times the 4,188.79 divided by 125, 33.51 centimeters cubed. What do you think? What's that? Okay. Yeah, so you got it down?
Yeah, I missed the whole step of squaring or cubing.
Okay.
That was a mistake.
Well, the good news is you're not going to get any new homework. The bad news is I'm about to give you a quiz. I'll give you the quiz now. You can work on it for the rest of the class period. Remember, you are all required to stay today for the bridge class so that you can get registered and we get all our paperwork done for it. If you would like to stay in the bridge class and work on it, that's fine. I'll just have you can just make a pile on the table here with them when you get done, or I'll be in the room here anyway.
This is not a quiz we can take with us.
This one you have to have turned in before 9:30 today.